Our next speaker is familiar in the circles of Fisher-Tropsch, and also is active in professionally in organizing meetings and being an editor too as well. And we can always count on Jerry Spivey for being there on time and getting things done. And we're pleased to hear from him as he talks to us now about CO2 methanation, or methane reaction.
Thank you, Bill. This is the first talk you've heard in this session that does not have to deal with Fisher-Tropsch. So with those of you coming to hear a Fisher-Tropsch talk, are going to be disappointed. I'm going to talk today about the methane CO2 reaction that we had published before leading to acetic acid. This work was done at NC State by Esther Wilcox, a PhD student, advised by George Roberts, who's at NC State, and myself. This is the reaction that I'm going to talk about today. It's a reaction with a very poor thermodynamic conversion, and that's one of the challenges experimentally. But it's also a reaction that I believe to be an important one. There's actually been a fair amount of work done on this, most of it reasonably recently. There was a South African patent belonging to Celanese that appeared back in '95 claiming only a certain selectivity and sufficient conversion with no data given and no catalyst described. More recent work by Taniguchi et al. Used vanadium aqueous catalyst and an oxidant in a trifluoroacetic acid, that's TFA, solvent. They obtained a reasonably high yield based on methane, but they also saw that the reaction took place even when no CO2 was present, which precluded the coupling reaction that I showed you in the first slide. We published a paper showing the thermodynamic feasibility of explaining that result by the decomposition of the TFA, and Mark Zarella and Alex Bell's group at Berkeley later confirmed that experimentally in a recent paper. There's also some work by Huang et al., and in that case they looked at a copper-cobalt catalyst and cyclical methane CO2 pulsing over the catalyst. They formed a wide range of products, including some cyclic compounds. They did form acetic acid, very low in selectivity, but it was observed. An interesting application of this that had not occurred to us when we began the work is that in a petroleum production process, there's actually a high enough pressure in certain wells to promote this reaction with a reasonably high conversion. And there was a series of papers published by Mike Gallenbach at Shell in which he looked at this reaction with the intention of applying it to petroleum production where methane and CO2 existed at the bottom of a well. In this particular system that he looked at, he used isotopic labeling and showed, at least in his conditions, that both carbons in the acetic acid came from a methane, and he also produced methanol. What I'm going to talk about today is some work that we did to look at how this reaction takes place on supported metal catalysts. We looked at several of them. One of them was a palladium carbon catalyst, one reduced, one not reduced, provided by Calgon with a nominal loading of 5%. We also looked at a corresponding platinum catalyst on gamma alumina provided by Johnson Method, prepared by conventional methods. I'm only going to talk for a moment about a few of those catalysts in which we saw the formation of the acetate group, or in some cases gas phase acetic acid. This is an unreduced palladium carbon catalyst, and this is the drift spectra that we saw, and this shows that when that catalyst was treated with CO2, we actually saw what we conclude to be the formation of the acetate group on the surface of the catalyst, although by mass spec we saw no evidence of gas phase acetic acid on this particular material. This is the drift spectra just showing the assignments of the wave numbers. The catalyst that turned out to be the most promising, and I'll show you some more results on this later, was the 5% platinum alumina catalyst. This is the drift spectra showing the result when the catalyst was exposed to a mixture of methane and CO2. On the right you see the acetic acid spectra on that same catalyst taken in the same instrument to convince you that we're forming acetic acid. And at the top on the right hand side is the spectra that we saw on that particular catalyst. This same thing shows the assignments of the wave numbers. These are the relative reactivities of these materials. First of all, we of course check the carbon support and the alumina support to convince ourselves that the reaction didn't take place solely on those materials. We did not see any reaction on those, nor did we see any on the reduced carbon, only on the unreduced. That's why I didn't show you any drift results from that catalyst. On the unreduced palladium carbon, we saw a little bit of evidence of the formation of the acetate group. It required a CO2 pretreatment in temperatures of around 400 degrees C for that to take place. On the palladium alumina catalyst, we saw formation at about 200 degrees C, and then the best catalyst was the platinum alumina catalyst, and we also saw the formation of gas phase acetic acid beginning at about 200 degrees C in that case. We looked at the differences in physical properties of these catalysts and trying to explain exactly what we saw. These are the surface areas and pore volume of these materials. Nothing stands out there, and we did not draw any conclusions about a correlation between the activity and these particular physical properties. We did see some differences, however, in the dispersion of the metals. Looking at the alumina-supported catalysts, 5% nominal loadings, we saw much higher dispersion of the palladium and platinum on those two materials than on the other catalysts. And I'll show you in a moment why we believe that to be important in describing the mechanism that we saw. We also examined this with CO2 and methane pulse chemisorption, and looked at the TPD of the materials after we had done the pulse chemisorption. This shows here the adsorption of CO2 on the alumina support, and as well as the other materials. I've highlighted the ones that I believe to be important, and that shows you that on the alumina supported materials, both palladium and platinum, we have a substantial amount of CO2 adsorption, at least relatively speaking, on the support, as well as on the two metal-supported catalysts. Okay, looking at the corresponding numbers for methane, we also see that on those materials that were active for this reaction, we see a reasonably high, at least relatively speaking, adsorption of methane on these materials as well. Particularly notice the difference here between the palladium and platinum materials. Same support, same metal loading, much higher adsorption of methane, particularly on the platinum alumina support, our most active catalyst, compared to that on the other materials. Okay, what I've done here is to compare the properties that I've just showed you on the reactivity of these materials as a function of the catalyst. What I'm going to show you is bars that represent the adsorption of CO, CO2, and methane for the different materials. Carbon support, no reaction, no adsorption. On the reduced palladium carbon, we see a little bit of CO adsorption, very little of methane or CO2, also no reaction. On the support alone, we see a reasonably high adsorption of CO2, but as we might expect, no reaction. The more interesting catalysts are the ones that we looked at last. First of all, let's look at the palladium alumina. We see a fair amount of adsorption both of CO2 and methane. We believe that's important. I'll show you that in a moment. And then on our best catalyst, we see roughly equal amounts of adsorption of methane and CO2, and that corresponds to the mechanism that I'll show you in a moment. This is the adsorption of CO2 on the alumina, just showing the results that from which we extracted the activation energy of desorption, which I'll show you here. These are the CO2 TPD results on the different materials, the alumina, the palladium alumina, and the platinum alumina. You'll notice that there is a similar activation energy of desorption for each of these three materials. I'm going to convince you, hopefully in a moment, that the CO2 adsorption takes place exclusively on the alumina support, but this is one piece of evidence in support of that. No significant difference in terms of CO2 TPD among these materials. That's consistent with that conclusion. However, the story is a little different on methane TPD. Here we have shown the spectrum at two different heating rates for methane TPD from the palladium aluminum material, two different peaks. Okay, let's look at the results on this. First of all, on the palladium alumina, what I've shown here is the temperature of the maximum of each of the two peaks, showing two different modes of absorption of methane on the palladium alumina and the corresponding activation energies of the desorption of that material. You'll see that there are differences between that and the platinum alumina, suggesting that there is some difference in the way that methane reacts with the palladium versus the platinum, perhaps explaining the difference in reactivity. Recall that we saw some acetic acid formed on both, but we did see a substantial difference between the palladium alumina versus the platinum alumina, and that's reflected here in the difference in the activation energy. TEM confirms the dispersion results that I showed you earlier. The palladium and platinum alumina are very similar. I've shown in the right-hand side the TEM for the platinum. And then on the right-hand side of the carbon, we see much lower dispersion in the case of the carbon support versus the alumina support. So let me conclude by postulating a working concept of what the mechanism might involve. First of all, we might imagine that the methane absorbs dissociatively on the platinum supported on the alumina. The CO2 absorbs solely on the alumina in close enough proximity with the higher dispersed platinum particles that there's an interaction between the two. We might then imagine that the acetate group is formed on the surface, as I show here in this next step, leaving a hydrogen atom behind that I'll show you in a moment is picked up by an adjacent group, okay, forming the acetic acid, which then desorbs. Okay, I'm not claiming this mechanism is correct. Pointed out by one of our earlier speakers today, mechanism Bert. Our mechanisms are always working hypotheses, but this at least is consistent with the data. It explains a number of things. It explains the absorption of CO2. Independent of whether platinum or palladium is present. It explains the effect of dispersion, how dispersion is necessary for the type of interaction that I've shown here, and explains the formation of the gas phase acetic acid. So let me conclude this by saying that we believe that the alumina supported absorbs CO2 and plays a role in the methane CO2 chemistry. The temperature maximum and activation energy for desorption of CO2 on the alumina is similar for all. I showed you that in one of the slides, that whether the palladium or platinum are present or not, the activation energy of desorption is roughly the same, indicating that the absorbed species is the same. That's not the case for the methane, however. Okay? Active catalyst for this reaction requires three things. It requires an active metal, presumably to dissociatively absorb and activate the methane molecule, CO2 absorption, and the methane absorption. Okay. The most active catalyst that we've looked at so far is the platinum alumina catalyst, and perhaps by coincidence, but you'll recall from the earlier slide that roughly equal more amounts of methane and CO2 are absorbed, at least as measured by TPD. The work that was done here was supported by the Science and Technology Center at NC State University, funded by the National Science Foundation, and an earlier agreement under the EPA Exploratory Research Grant also carried out at NC State. Thank you very much.
We have time for a few questions. Please.
Yeah, Kurt?
Yeah. In a speculate, you're showing CO2 absorbed, but not as a carbonate, and down to the surface through something, which probably isn't an oxygen because it isn't a carbonate, or you have to suggest that there is. that's catalytic gas, it's on the alumina, but you have some oxide vacancies on the alumina, possibly, and maybe these could be, go back to what spillover did at one point, and actually spillover would actually reduce the alumina surface and give you active sites. And maybe that's the part of the puzzle that you haven't filled in, is how you got there and how you could get an active alumina. Because most surprise, obviously, and I'd like you to speculate on where methane absorbs the alumina and how it absorbs the alumina.
I don't think, that's...
No, you showed data that showed on pure alumina, you had methane absorption, which wasn't trivial. And it was more than you got on some of the other catalysts. Straight methane absorption of alumina you showed today.
Okay, let's go back.
Data speaks.
All right.
Data speaks.